Welcome to this class on deep learning. Today we're going to talk about LSTMs and some more details on how to use them for encoders and decoders. So this is the second part on sequence models. But first, let's actually look at how one would go and implement a recurrent neural networks language model. So this is useful not just for the RNNs right now, but also later on when we go to transformers and other mechanisms for sequence modeling. They build and draw heavily on this general paradigm. So the first thing that we need if we want to encode a sequence is we need to map the input tokens into some vectors. And as we already talked about before, you could either use individual characters, or you could use subwords, or you could use words. And that level of granularity depends a little bit on the amount of memory that you have available, but also what's the right representation for the right amount of data. So for instance, Amazon Web Services might be a token that occurs so frequently that you might encode it as its own, but maybe for the word heteroskedastic, you might want to decompose this into hetero and skedastic, because there's also homoskedastic. And essentially you want to use the available language itself to give you a good way of identifying subwords. These are basically frequent subsequences in order to then encode the data. In any case, so we take our input stream, we map it into some appropriately granular components, and so we get one-hot encoding. So these are vectors that are just all zeros and 1, 1. You might not necessarily want to instantiate this way, but anyway, let's just assume that. And then you go and furthermore multiply this by an embedding matrix. So this is now really an embedding to some d-dimensional space where each input token corresponds to a different vector. Okay, so this is this in pictures. Let's say we have the time machine and we decide to go and pick some character encoding, and for whatever reason we've picked the vector 1 and then all zeros to indicate t, then h to be the vector that has 1 bit set on the second digit, and so on and so on. So we get this vector, we now multiply it with an embedding matrix, and then we get those embedded vectors v prime. Okay, so this is what the recurrent neural networks can operate on, because now we've moved from the domain of discrete symbols to one of vectors. Okay, so this is our input sequence. We then get a vector sequence of hidden states, h1 through ht, and ht is given by some function of the previous hidden state and the current input. And then after that, I get an output sequence, which is generated based on that hidden state, possibly also other things. And so basically I go and read the sequence to generate hidden inputs, then start generating outputs, and I keep on doing this. And if in the end we need to map into discrete symbols again, then I get my output vectors and a corresponding decoding matrix w prime, and then I can, for instance, model p of y given o to emit specific characters. Right? And now each of those characters is essentially treated as if they were independent, but they're treated as if they were independent conditioned on whatever happened before. That's just for matters of convenience. Obviously, they're not independent of each other because you're generating one after the other, and depending on how I'm setting up my model, I may actually condition the next emission based on what I've emitted so far. So for instance, in machine translation, you would want to use the emissions that you've made so far to decide what to emit next. Okay, so now we have this rather complex machinery. So going back. So we have the input encoding, we have our RNN, and then we have the output decoding. And so now we need to optimize over this. And for instance, if we take a character encoding, it's not that uncommon that I might have, tens to hundreds of characters in a sequence. So if I run backpropagation through that, because the first state really affects what happens later, then I need to keep a lot of intermediate values in memory. That's just because I have a large number of states. And the problem is I thus get a autoregressive model with over maybe, tens to hundreds to thousands of states. And this can lead to a lot of really brittle effects and almost like butterfly effect style dependencies. And the gradients can vanish or they can get really large. And so I need to have a couple of mechanisms for dealing with this. One is I can simply truncate the gradient. So what I do is I still keep the direction the same, but I simply upper bound the norm of it. And that can easily be done by this operation here, which maps g, the gradient, into the minimum of 1 and some parameter theta over g, the norm of g times g. You can easily check that this means that the length of the clipped gradient will never exceed theta. Okay, so that's one thing. And there are other tricks, such as simply truncating our backprop chain after some time. We'll talk about this later. But all those tricks are necessary in order to make sequence models actually work in practice. The other thing that we need to do is we need to measure how well we're doing. And if you think about it, so far we basically looked at the log likelihood for multi-class classification, or maybe a least mean squares problem for regression, which actually can be mapped into something that matches a log likelihood. But anyway, but the problem is if I have sometimes short, sometimes long sequences, maybe in a machine translation model, then it's really difficult to compare sequences. So for instance, if I have some nonsensical sequence like she table versus this is a nice and beautiful white table, then those two sequences, well, the first one may very well have a higher likelihood, because even though the character combination is bizarre and unique, it may still be more likely to occur than a weird combination of characters that I would get otherwise. And so as a result of that, I need to have some mechanism to calibrate the log likelihood by the length. And this is very simple. All you do is you take the negative log likelihood of the entire sequence, divide it by the sequence length. And so with that, you're effectively counting the number of bits that you need to spend per character. So, and that's actually a good way of encoding a sequence. So that would be like asking, what's the compression ratio that my model gives me for the data relative to what the model predicts? So if I, for instance, then have like a, length normalized log likelihood, that would be, might be maybe 2-bit. That just means on average I have, a surprise of 2-bit per character that I encounter. That's not necessarily saying that I have that surprise at every single character, but on average across the length. Perplexity is the exponentiated version, so that's basically the possible number of choices on average. So if I have, perplexity of 4, that means, there are 2 bits that I can, on average, spend, right? Anyway, so this is a convenient way of making sequences of different length comparable to each other. Okay. Of course, now let's get back to the issue of, those very long sequences, because besides the objective, we also need to fix the optimization problem. So if you recall, in a recurrent neural network, we have this sequence of observations, then the corresponding explanations, and then the output. And in the hidden state, well, we update ht is some f of ht minus 1, xt minus 1, and w, and then I get the output ot. Okay. And if I want to compute the gradient, well, I have this very, very long sequence, right? So here's, for instance, what happens if I were to compute the gradient of the hidden state at time t with regard to w, then you get this very long sum of a very large number of products of gradients just due to the chain rule, right? So if I want to get the gradient of the green circle relative to all the parameters, I need to walk through the entire chain as it goes from start to finish. Okay. This is bad because it's computationally very costly, numerically unstable, and so on. And so rather than computing the sum over all terms I equals t equals 1 to t, or actually going from t to 1 backwards, right? I just stop at some point, and that's it. So this is called truncated backprop through time. The way this works in a deep learning framework is you just detach the corresponding operations from the gradient computation. So you detach the computational graph, and that way AutoGrad does the right thing. Now you might wonder, well, this is quite terrible. Can you actually do this? And there are a couple of reasons why it's not such a terrible idea. First of all, it actually makes things a little bit more robust because now whatever happened a very long time ago shouldn't directly be, or whatever state representation I had a very long time ago, rather than that, shouldn't affect so much anymore what I have now, at least in terms of how I got to that state representation. Right? I'm still using that state representation to update the new models, but at least I don't want to influence how I would have represented things a very long time ago. That adds some robustness. And there are ways on how to make this mathematically more kosher by having a variable length truncation and then weighing things accordingly. You can prove that this leads to an unbiased gradient estimate. Unfortunately, in practice, it doesn't really make much of a difference in terms of training. So while it's nice to know that you can make this mathematically more clean, in practice, don't bother because you don't win from it. Okay. So now that we have all this machinery set up, let's actually see how to build those autoregressive models. And the first thing to look at are those things called gated recurrent units. And I mean, historically, they actually post-date LSTMs, but they're a simpler version. They're actually an attempt of simplifying LSTMs. And in many cases, they're all that you need. So the idea is if you have a long sequence of observations, not all the observations are equally relevant. So you only really want to remember the relevant ones. And what that means is that I need to have two mechanisms to update my hidden state. One is a mechanism to decide when to pay attention. And the second mechanism which tells me when to forget about things. So I need basically an update gate and a reset gate. Okay, so let's model this. So we have an input and we have a hidden state, ht minus 1. So that's my previous hidden state. And I simply have, some sigmoid and then just the simple perceptron version of a reset gate and update gate. So these are just, linear functions of xt and ht minus 1 that I now use to update and, control those functions rt and zt. Okay, so this is fairly straightforward. Now, this allows me to generate a candidate hidden state. So this reset gate allows me to multiply my hidden state with the values of the reset gate. And I concatenate this with, the input state, and it gives me a new candidate hidden state, h tilde. And, for convenience, I throw a nonlinearity at it. So in this case, a tanh to keep the full range. In any case, so I get something where I'm gating, how much I still want to carry over of the previous state, and how much to incorporate the current input. Okay, so this gives me a candidate hidden state. Now the next thing is I need to make use of the update gate itself, and I'm doing this by appropriately taking a convex combination between the original hidden state and the new candidate hidden state. So that's what this 1 minus and times expression is. So this is a very complicated way of just saying I'm taking a convex combination between ht minus 1 and ht. Okay. So in short, we have two steps. We have a reset gate, which tells me how much to incorporate of the hidden state in the new candidate hidden state, which has some nonlinearity, and then a convex combination between the old state and the new one. So in its full glory, these are the equations that give me the GRU. So gated recurrent unit. And in many cases, this works very well. And more importantly, the GRU is computationally a little bit more efficient than the LSTM, so a lot of people use it. Okay. Now to the granddaddy of all these recurrent models, namely the long short-term memory. And this was introduced by Hochreiter et al. And when they introduced it, they modeled it on a flip-flop. So a flip-flop is an electronic circuit which basically can store 1 bit. And what you have is you have 2 gates, namely an input and a write gate. And the input gate basically allows me to set the value of the flip-flop, and the write gate will allow me to decide whether I should actually incorporate this input. And then the output is just that. Now I may have an output gate which allows me to decide whether to actually read out from that flip-flop at all. So unlike before, where we just had, the hidden state and then the mechanisms to update this, here we actually have a separate output gating function to decide whether I can read. Okay, so in short, I have a forget gate, which allows me to shrink the values towards 0. I have an input gate, which decides whether we should ignore the input data, an output gate, whether I'm actually allowed to read out from it. And that's what gives me the full LSTM model. Okay, so let's actually build this up separately. The other peculiarity is that there are actually 2 different types of hidden states. There's the outright hidden state, and then there's the memory state of the LSTM. You might ask, whether these are the only ways how to parameterize those latent variable models. And as a matter of fact, that's not really true. There are lots of other choices, and people have tried to optimize over them. Turns out that despite the optimizations, there are no others that have really caught on as being far superior in terms of computational performance or accuracy. So by now, people kind of use either LSTMs or GRUs and call it a day. There are other places where there's maybe more exciting innovation. Anyway, so to model the gates, what I get is I model the input gate, the forget gate, and the output gate just as a simple sigmoid function and a multilayer, just a simple perceptron of the input and the hidden state, right? This is very similar to before, except that before that we had only, an input and a forget gate. Now we also model the output gate. The next thing is we model the candidate memory. So this is similar to the candidate state that we had in the GRU, and this is modeled by a tang, right? And then what I do is I now use the forget gate to multiply the memory that I had before with a forget gate. So this allows me to reduce the amount of things that I remember. And then I also modulate appropriately the input gate output with the candidate memory to decide, how much I should trust the new memory. So one down regulates the old memory, the other one down regulates the new memory. And then I go and combine those and I get the new memory state. Okay. Now the last thing is I have an output gate, and the output gate, so this is exactly what we had here. Now the output gate, HT, allows me then to update my hidden state. So I take my original hidden state, I have this nonlinearity for the output gate, I get then the memory state, and this gives me the new hidden state. So note, and this is quite different from before, while the memory state essentially doesn't get modified too much because I have just additions and multiplications, the hidden state itself is entirely newly computed after running it, combining it with the input state through the output gate, then combining it with the memory state, and this gives me a new hidden state. So if you will, the memory has a little bit more of the original data preserved, and the hidden state, well, a little bit less. The details are really not that important. Suffice it to say, any self-respecting deep learning framework would have a workable LSTM implementation available that you can just use by just using RNN LSTM as one of the terms. So in sum, what you have is you have a general sequence encoding and decoding framework, right? So you take the original characters, you use an encoder for symbols, you take the latent state, you do all the updates there, and then you emit and possibly feedback if needed. To train things, truncated backprop through time is really important. Mind you, for graphs, you then end up using that for more structured objects. For GRUs, so gated recurrent units, you only have a simple latent state, and it's computationally more efficient. LSTMs have a little bit more complexity. They have two different types of latent states. That's mostly for historical reasons. And basically go whichever and use whichever one matters. It works better. In practice, you're probably better off worrying more about, whether you should use a bidirectional model, whether you should use attention, what depth you should be using. And if you can afford it, go probably with an LSTM. That's probably a slightly more powerful and safer bet. There's a lot more to this than what I can cover in 20 minutes in a crash course. So please check out the corresponding book chapters. They have a lot more notebooks in there, and you can read up on all the references and details.